Okay, 6.1, estimating with finite sums, or Riemann sum. So now we're doing the second part of calculus called antiderivatives or integration. So I'm just going to read to you really quick 6.1, the first paragraph in 6.1. The need to calculate instantaneous rates of change led to the discovery of calculus, to investigation of slopes of a tangent line, and ultimately to the derivatives, to what we call differential calculus. But derivatives revealed only half the story. In addition to calculation method, to describe how functions change at any given instant, they needed a method to describe how these instantaneous changes could accumulate over an interval to produce the function. That is why they also investigated the area under the curve, which ultimately led to the second main branch of calculus, called integral calculus. Once Newton and Leibniz had the calculus for finding slopes of tangent lines and the calculus for finding areas under the curves, two geometric operations that would seem to have nothing at all to do with each other, the challenge for them was to prove the connection that they knew had to be there. The discovery of this connection, called the fundamental theorem of calculus, brought differential and integral calculus together. So now, for the next couple of chapters, we are going to be dealing with area under the curve. So, a train moves a track at 75 miles per hour from 7 to 9 a.m. So this is miles per hour, 75 miles per hour. This stands for the time from 7 to 9, and draw a line up to there and draw a line to there. It makes a rectangle. The height of the rectangle is 75 and the width of that rectangle is 2. So it's 150 miles it traveled. So basically, in order to find the total distance traveled, what is the total distance traveled is another name in calculus to find the area. And to find the area of a rectangle, it's just width times length. The ones that we are going to be studying throughout this rest of this calculus is the shapes might look like this, or the shapes might look like this. And you have to find the area of those types of figures and not rectangles. And that's why they came up with using little rectangles. Riemann, a mathematician, used little rectangles to help you find the area. So, Newton's way is this. If a velocity varies over the time A to B. So let's just go like this. And we're going from A to B. Okay, I'm going to read it one more time. If the velocity varies over the time AB. Velocity means derivative. This is an f prime of x graph. This is a derivative graph. If you draw the line down and down here, the shaded region is the total distance traveled. This area in here is called the total distance traveled. And to find the total distance traveled, all we're going to do is find the area. And I'll just keep reading this page. This sparked the interest in finding the area under a curve. Imagine breaking this time interval up into many parts. So we're going to break this little area from A to B up into little rectangles. This is called Riemann sum. Okay, so here we go. A particle starts at x equals 0 and moves along the x-axis with the velocity of vt of equals t squared. Read the fine print this is the velocity, or this is the derivative equation. And if you graph this parabola, everybody knows that t squared is a parabola, but they want you to graph it when t is greater than 0. They only want this part of the parabola, and we want to go out to 3. You need to draw the line from 3 up to your parabola. And basically what we're going to do is find the area of from here to here to here. And there is no formula in geometry. It's not a triangle, it's not a rectangle, it's not a circle. So we're going to use the rectangle or approximation. Riemann invented using rectangles to find the area. There's an MRAM, an RRAM, and an LRAM. And what I'm going to do is I'm going to show you the 3. So here's that parabola from up above. Here's that parabola from up above. And here's that parabola from up above. And I'm going to show you the left hand rectangular approximation method, the LRAM first. And then I'm going to show you the RRAM, the right hand rectangular approximation method, and then the midpoint rectangular approximation, MRAM. Okay, so basically, here's 3, remember? Here's 3. So basically today, you're going to do one of these depending on which one they ask you to do. When they want you to put rectangles in, if they want you to put rectangles in here, and they want you to have the left side of the rectangle touch. The left side of the rectangle touch. So they want this tip, the left side, to touch. This one, they want the right tip to touch your line. The right hand rectangular approximation, or they want you the middle of your rectangle to touch. Depending on what part of your rectangle do they want you to touch. And they want the left ones to touch. So I'm going to try to fit these in here the best I can. I'll use green. Watch how I'm putting these green rectangles in. Are you noticing that the left side of the rectangle is touching? And now I'm going to put the right ones in. Whoops, that's a little wrong here. That wasn't supposed to be there. Let's back it up. Do you notice that the right tips are touching the curve? And then trying to put the middle ones in, I'll try to do my best here. I'm going to change it to again. See that the middle of the graphs. So basically what they figured out by looking at the area, this is going to be an underestimate for the area, obviously, because there's gaps. This is going to be an overestimate. And they figured out that the MRAM is going to be the most accurate. I don't know why they're teaching you all 3 of these. This is an underestimate, this is an overestimate, and this is the most accurate estimate. Why don't we just learn this way? You will get tested on all 3 of these, so make sure you know how to do all 3 of these. Okay, moving on. Oh, let's go up and do it now, sorry. Let's go do it. So, we're going to break this up. They're going to tell you how many triangles you're going to, or rectangles. We're going to break this up into 6 rectangles. And we're going to do the LRAM, the RRAM, and the MRAM. This is very time-consuming assignment. So I need to break this up into 6 rectangles, and I want to go out to 3, so I need to put another one here, here, and here. So I'm going to be counting by 0.5, 1, 1.5, 2, and 2.5 are my dashes. And what I'm going to do is I need to put 6 rectangles in here. You can count them, 1, 2, 3, 4, 5, 6. I'm putting 6 rectangles in there. And I'm going to do the LRAM. And if you use rectangles, you need to have width and length. Well, the widths are all the same. If you look at all the rectangles, it goes from 0 to 0.5, 0.5 to 1, 1 to 1.5. All of the rectangles have the same width. So they usually just put that on the outside. The lengths change. This one's a shorter one, then it's tall, and that's even taller. The length is dictated by what the curve is doing. This stands for the length, basically, of your rectangle. So what you have to do is, specifically at the 1 marker, this rectangle, right here, well, at the 0.5 marker, sorry. At the 0.5 marker, you're going to put 0.5 up into this equation and square it. And you're going to get 0.5 times 0.5 is 0.25. And then, but you started at 0 first. And we're doing the left side. So if you're doing the left side, you need to use 0 first. And you're going to put 0 up into there, then you're going to put 0.5 up into there, and then you're going to put 1 up in there, and then you're going to put 1.5 up into there, whatever 1.5 squared is, and then you're going to put 2 in there, and then you're going to put 2.5 up into there, and square it. You don't use the 3 because you are doing the left part of your rectangles. And then you add that up, and this is going to end up becoming 6.875. And then if you do the right RAM, you start on the right side, and if you look at the rectangles, you're using the first right point, and the first right point is not 0, it's 0.5, 0.25. And then after 0.5 is 1 squared, and then it's 1.5 squared, then it's 2 squared, then it's 2.5 squared, and then it's 3 squared, which ends up equaling 11.375. And then the last one is the midpoints. So what I need to do is make myself a chart to do my midpoints. I know from 0 to 0.5, 0.5 to 1, 1 to 1.5, 1.5 to 2, 2.5 to 3. I know that my midpoint needs to be 0.25. And I know that my next midpoint is going to be 0.5, and you just add them up and divide by 2 basically, which is 0.75. And then this is going to be 0.75. And then halfway between, it's going to be 1.25. It's going to be 1.75. And those are the points that you have to plug in there. So this is going to end up being 0.0625, because you have to take this and put it into your t squared. You have to put this and put it into your t squared. You have to take this and put it into your t squared. And then you have to take the next one and put it into your t squared. And then you take your next one and you put it into your t squared. And then you take your last one and you put it into t squared. And you are going to get for the midpoint rectangular approximation is 8.9375. As you can see, this is an underestimate, this is an overestimate, and this is the most accurate one called the midpoint. We're going to do more of these. I just wanted to show you all three of these on the same page. Okay. So here's a new one. F of x is equal to x squared sine of x. So I'm just going to show you what it looks like. It looks something like that from 0 to 3. So that's what x squared sine of x looks like. Remember, this is a velocity graph. This isn't really f of x, this is really f prime of x. That's why it gets a little bit confusing. They want you to break this up into 5 intervals. 5 intervals. So 3 divided by 5, you're counting by 0.6. So 1.2, 1.8, and 2.4, and then 3. And they want you to use the midpoint one to do this problem. Well, you can, if you put the rectangles in here, I'm just going to do it really fast. They're supposed to be touching up there. If you're going to put the 1, 2, 3, 4, 5 rectangles in there, they all have the same width. They all have 0.6 as its width. As you can see, the lengths differ, and the lengths differ. This is now the length formula. It used to be t squared. This is now the new length formula. Sometimes it makes a very big rectangle, sometimes it makes a smaller rectangle, but this dictates the length, and they want you to use a midpoint. So from 0 to 0.6 is the first width, the midpoint is 0.3, and then 0.6 to 1.2, the midpoint is 1.8. Oh, I forgot to divide by 2, sorry. 0.9, sorry. And then 1.2 to 1.8. .5, 1.8 to 2.4. It's going up by 0.3, so this is going to be 2.1, and this is going to be 2.4. What you have to do is you have to stick this 0.3 into this equation to find what the length is. And it's going to end up being 0.0266 when you plug 0.3 in. When you plug 0.9 in, it's going to be 0.63449. And you plug 1.5 in, you're going to get 2.2444 plus 3.8068 plus 3.1156, which equals 5.897. That's if you did the midpoint. That's if you did the midpoint. Let's say they wanted you not to do the midpoint. Let's say they want you to do the left RAM, the left side. If they want you to do the left side, the width is still 0.6, but you have to look at the left side of each one. The first rectangle's point, you need to plug 0 into there. So you need to plug 0 in to get the length. The next one you're going to put in is 0.6 into the next one. And the only number that you don't use is the 3 for the left RAM. And to the RRAM, you don't use the 0, but you use the 3. So, okay, now how do you read a table for the AP test? It's the same thing if you read a table. This stands for your width, and this stands for your length. And let's do the RRAM method, the right side. So if you're doing the right side, the widths are all 2. And if you think of these numbers, 0, and then 0.6, and then 1.4, all the way out to 1.7, and you're doing the RRAM, you're going to use this one, and this one, and this one, all of the numbers except 0. So you're going to add these all up, 1.7, 2.9, 3.8, all the way down to 0.6 and multiply it by 2. And it's going to end up being 41.8. Okay, next problem. Trying to get on of this here. Okay, I think we're on the last slide. Nope, one more slide. Page 271, I'm going to do the example with you. Instead of finding the area, they want you to find the volume instead. Well, you know area is width times length. You know volume is width times length times height. So, instead of using rectangles, which is width and length, they want you to use cylinders instead to find the volume. So, I'm sorry. They want you to use a cylinder, which is volume is equal to pi r squared h. So, in number 271, the equation is y equals the square root of 16 minus x squared. And it looks like this. And if you connect your dots from a -4 to a +4, again, remember that this is a derivative graph. And they want you to find the volume of this. If they asked you to find the area, you would be putting rectangles in there. But instead of using volume, we want to put cylinders in there. And if you look on page 271, they have a nice picture of what the cylinders would look like. The cylinders would be put in like this. And the next cylinder would be put in like this. So if you look at this sideways, the volume is equal to pi. The height of all the cylinders are the x-axis. The height is the x-axis, and the radius is really the y-axis. And if you're going from a -4 to 4, and we are going to do the left RAM. So the left one, we're going to put we're going to put a -4 in there. When you plug a -4 in there, the height goes, we're going to put how many cylinders in there? We're going to put 8 cylinders in there. We're going to put 8 of them in there. If you're going to put 8 of them in there, the heights go up by ones. If you, from a -4 to a +4, you're going to put 8 of them in there, your heights go up by 1, and your radius is dictated by what, it keeps getting bigger and bigger. And the first one you're going to put in is a -4, and you're going to square it. Sorry, we're going to put it into here though, sorry. We're going to put a -4 into here. And then we're going to put a -3 into there. And then we're going to keep doing, and we're going to put a -2 into there. And then we're going to put a -1 into there. And you're going to keep going. Since it's the left RAM, the only one you're not going to do is the 4. So the last one you're going to put in is this one. And it ends up equaling, I don't know what I have. I don't have the right answer. I can look on page 271. Let me look to see what the volume is. The volume ends up becoming 268.083 cubic units, whatever it is. Okay, and the last set of notes are, if it's an increasing function, RAM is an overestimate. If it's a decreasing function, RAM is an underestimate. If it's an increasing function, LRAM is an underestimate. If it's a decreasing function, LRAM is an overestimate. And really quickly, how do you find the MRAM? These are the steps in order to find the MRAM. And that's it for 6.1, using a bunch of rectangles to find the area under a curve.